Hi everyone. In this lecture, we're going to be talking about sound. Now, sound is a form of energy, just like heat, just like electricity, etc. Sound is a form of energy. Okay, so let's take a look at this. So, to start with, let's think about, again, we're going to remind ourselves of waves, but we've got some new things going on here with this wave. Okay, we already knew that wavelength, well, one, we already knew that we've got crests and troughs in a wave. So we have crests up here, troughs down here. We already knew that the distance from crest to crest would be a wavelength, or from trough to trough, that's a wavelength. And the number of crests that are passing by a particular point in 1 second would of course be the frequency of the wave. Well, let's take a look at a couple of other things that we need to know here. One, the distance from equilibrium is the amplitude of a wave. Okay, so the amplitude of a wave is the distance, this distance right here from equilibrium, the zero mark, to the highest point would be the amplitude. Now, obviously, that's also exactly the same as from the equilibrium point to the very bottom of the trough. And so that's amplitude. And then I just use the other term, equilibrium position, which is right here in the middle. So we have the period of a wave is the amount of time necessary for an entire wave to pass. And for the entire wave, it's essentially crest and trough. So we have the frequency of the wave, which is the number of crests that are necessary, the number of crests that pass by in a certain amount of time, typically 1 second. And then the period of a wave is going to be how long it takes for one full wave to pass. So, looking at the definition of some of the definitions that we need to know for sound. The pitch of a sound is going to be related to its frequency. The frequency, that would be the number of waves that are passing by, the number of crests that pass by in a given amount of time, typically 1 second. So the frequency of a sound wave is going to determine the pitch. Now, the pitch of a sound, think about what that means, whether it's going to be a higher pitch or a lower pitch. If I can try to do that right. High pitch sounds would be things that are way up high. Lower pitch sounds are way down here. So the higher the pitch, the higher the frequency of the sound wave. Intensity is a measure of how much energy is carried by the wave. The wavelength, okay, we already knew the definition of a wavelength. So this is the distance between successive wave crests or successive troughs. Okay, the amplitude of the wave is the size of the wave from rest. That is the distance from the equilibrium point to the highest point on the crest or the lowest point in the trough. That's the amplitude. The frequency of the wave is the number of cycles of the vibration of a wave occurring in 1 second. So the frequency is essentially the number of crests that pass by in 1 second. So how do some of these translate into what we hear when we hear a sound? Amplitude. The amplitude of a sound wave is going to relate to the volume. Okay, the amplitude of a sound wave is going to relate to the volume of the wave. Okay, the volume of the sound that you're hearing. The louder the sound, the higher the amplitude. Pitch is going to be related to frequency, meaning that you'll have, and also you could see that in wavelength, because the higher the frequency, the shorter the wavelength. And then the period of a sound wave is going to be the time required for 2 successive crests or other successive parts of the wave to pass by in a given point. Time required for 1 complete cycle of a wave. That is, in order to go from how much time it takes for a full wave to pass by. When we're measuring frequency, remember we're talking about how many crests will pass by in a second, typically. And then if it's not, you could compare that to the period. So the wave itself. Sound is a mechanical wave. It's a mechanical wave because of the fact that it requires a medium. Sound itself is a compressional wave. In order for, when that compression happens, you literally compress compress particles in the air. They compress and they move apart, compress and move apart, compress and move apart. Okay, that's compression and rarefaction, and we'll get to that a little bit sooner in just one moment. But the point is that it's mechanical. There has to be a medium for the sound wave to travel through. If there's not, the sound wave won't travel. In other words, if you're in space, you're not going to hear any sounds. So whenever you see these, wonderful space movies and whatnot like that, and it shows something blowing up way over there, you wouldn't hear that. You wouldn't be able to hear that sound because sound isn't going to travel through space. Sound doesn't travel through space because there's nothing there for it to travel through. Now, what about sound traveling through something besides air? Of course, sound travels through water. Because water actually is more dense than air, sound travels much faster through water than it does through the air. This is why when you're underwater, you have a very difficult time pinpointing where a sound is coming from, and sound comes at you very rapidly from all directions because sound will travel through water faster than it travels through air. The same thing is true for solids. If you put your ear to the floor, you're going to hear things going on in other places that are touching the floor a whole lot easier than if you're standing above the floor. So sound is a mechanical wave. It requires a medium for propagation. In other words, it requires vibrating molecules. This is kinetic energy. It moves through a medium. The medium remains in place, but the energy is transmitted by the wave. It is a longitudinal wave. We do have longitudinal waves, and we also have transverse waves. Okay, longitudinal waves are compressional waves, and then transverse waves are waves that literally move up and down like the waves coming in on the beach. All right, so let's take a look at some of the differences here. A longitudinal wave is this. Now we can actually depict any kind of a wave as a longitudinal wave, but some waves literally are longitudinal waves, and so you could take a look at this oscillation moving back and forth. Okay, this longitudinal wave, we're depicting this longitudinal wave as, or we're taking a look at this mode of propagation here. We have compression and then it moves apart, compression and then it moves apart. So as we're looking at this, the compression, or as it's moving apart, it's up here and then it compresses and then moves apart and compresses and moves apart. And so we were able to take this longitudinal wave and demonstrate it here as a sinusoid in this manner. Sound is this kind of wave, this compressional longitudinal wave. Okay, and you can see over here exactly what's going on. The oscillation here is in a direction where we're moving into it and then out, in and out, in and out. Okay, so if you think about a slinky, compressing and then moving apart, compressing and moving apart, and that's what this wave is. So in longitudinal waves, the vibration is parallel to the wave to the direction of the wave is actually moving. So the particles come together and move apart, come together and move apart, come together and move apart. And this is a compressional, we call it a compressional wave or a longitudinal wave. Sound waves are this type of wave. We can also have a transverse wave, which is a wave that literally looks like this. And this is where the wave itself is moving in perpendicular to the direction that the wave is propagating. Think about if you have a slinky and you wave it up and down, or if you have a water hose and you lift it up and you pull it back down real quick, and then you get this wave that moves outward. And this is like the waves that are coming into the beach, actually, at the top, the surface waves that are coming into the beach. So this would be a transverse wave where and you can see in this animation right here, the wave of oscillation, the oscillation of the wave is perpendicular to the direction that it's propagating. Okay, so it's moving up and down as it moves forward, where instead of going back and forth and back and forth. So a transverse wave moves up and down, whereas a longitudinal wave or compressional wave moves in and out and in and out. Surface water waves actually have a combination of both. Typically, surface water waves are more of the transverse wave. Waves up underneath the water are going to be more compressional, and so you can actually measure that difference. But the particle motion is circular when we're talking about waves in the water. Waves in the air are typically just going to be longitudinal waves, like the waves that a tuning fork creates. So you get a series of compression or condensations and rarefactions, which is when it moves apart. So compression and rarefaction, or you could call it condensation and rarefaction. And this would be our longitudinal wave or our compressional wave. Okay, and you can see it here in the particles. So the condensation, rarefaction, or compression and rarefaction. So both terms are applicable here. And this is what a sound wave is when it's moving through a solid or moving through the air. So whenever we hear things in the air, we can only hear, there are only sounds that are in a certain range that we can hear. If it's too high or too low, we're not going to be able to hear it. We might be able to feel it, but we're not going to be able to hear it necessarily. So the typical range for human hearing is between 20 and 20,000 hertz. Infrasonic, meaning below sonic, is going to be anything that's below 20 hertz. This you might feel. Okay, I scuba dive, and oftentimes I've come across a large fish that's called a Goliath grouper. It's a huge grouper, and it can vibrate its operculum, which is the covering on its gills. And when it vibrates that, it creates an infrasonic sound that you can literally feel traveling through your body, which is kind of a cool thing. But that's its way of telling you you're getting a little too close. You might want to back away. When we hear, or you may also have ultrasonic sounds that may be heard by other mammals and just not like us. And they can also be used for imaging, because as the sound waves bounce off of something, we can actually create an image with that if you have the right equipment. Dogs and cats and other types of mammals can hear sounds that are above 20,000 hertz, and those are in the ultrasonic realm. And we talked, if you will recall, in the lecture of the human body, and you can go back and take a look at that, we did talk a bit about the mechanism by which you hear with your ear, looking at the bones of the middle ear and how it connects the outer ear to the inner ear. And the liquid that's in the cochlea and the hairs that are there that actually lead to the auditory nerve going to your brain. And so here you can see that. So the ear canal here vibrating the tympanic membrane, vibrating the malleus, the incus, and the stapes, which vibrates the oval window, which moves the liquid, the fluid inside the cochlea, and vibrates the hairs here, which will then stimulate this auditory nerve and send a sound to your brain. So when we visualize sound waves, okay, we can visualize them coming like this. Okay, you can think about it being a spherical wave moving out from a source in all directions. Most sound is omnidirectional. Some sound is going to be very directional. Think about the difference between listening to, say, a trumpet play. That's going to be very directional, because whatever direction the bell of the trumpet is playing, that's going to be the direction of the sound. It sounds very different if you're at the end of the bell in that direction than if you're behind the person. Whereas another instrument, like say a flute or a saxophone, is more omnidirectional. The sound is moving in all directions from the instrument, as opposed to simply in one direction. So a sound wave's spherical, moving out in all directions, and each crest is a wave front. So those crests are going to hit you, and that's what you sense as a sound wave. Sound can be reflected, refracted, or absorbed. Oh, that sounds an awful lot like light waves, doesn't it? We talked about that with light. Sound can be, all of these things can happen with sound as well. Sound can bounce off of something. That's an echo. So if you create a sound in a canyon or in some place that has really, really good acoustics, you might get an echo that comes back. That's a reflection. Sound could be refracted, meaning that it will move around things, so that it will change as it moves from one medium to another. And then sound could also be absorbed by a thing. You've ever been into, like in a theater, there will be sound absorbing material, usually in the back of the stage, so that the sound will be absorbed as it's going back. Or if you're in a practice room in a school of music, you might find that you're going to have soundproofing on all of the walls, and that's going to help absorb the sound. Now, one of the things that we find is that with the lower the frequency, that is, the longer the wavelength, the easier it is for the sound to travel long distances. It's easy for it to move around objects. In other words, it's easy for it to diffract around objects. And that's one of the reasons why that infrasonic sound is used by a lot of large animals to communicate across vast distances. Whales, for instance. Elephants on the land will communicate with infrasound, and it will travel for long, long distances across the plains. Boundaries between materials will cause a change in sounds. Between regions of the same material under different conditions, temperature and pressure will affect sound. So here's reflection. So you might have an echo. Sonar also makes use of sound reflecting. It will send a signal to, say, the bottom of the ocean and then back. Or if it's using sonar to determine if there's something in front of it, it may send out a sound wave, and as that bounces back, it will give the distance, however long it takes for the sound to get there and bounce back. That will actually give you an exact measurement of how far away something is, whether we're talking about another boat, or the bottom in this case right here. So waves rebounding off a boundary is called reflection. If it bounces back over and over again, you might get something called reverberation. You can get an echo. That echo can be diminished over time. So using sonar, ultrasonic imaging, this echo effect is how we create a visual image with sound. Refraction. When sound travels in different speeds through warm air and colder air, and so if we think about warm air sound travels faster, and so you're going to get this sound, literally you're going to get sound bending, and so it's going to carry differently in warm air than cold air. And that's because the sound moves from one temperature of air to another temperature of air, the speed actually changes. So if it slows down the sound, then the sound's not going to carry quite as far. And if it travels faster, the sound is going to speed up. And so you can see how that affects the sound of an airplane depending on where the warm air and the cold air is. If you have colder air closer to the ground and warmer air up top, then you're going to hear a sound if you're closer to the ground, the airplane, and then vice versa if you have a temperature inversion. Sound waves can interfere with each other. You've probably heard of devices that are called white noise devices or sound canceling earphones.